Hi, this is Kai Yang, and this is a schematic from our lock controller for design project number 3. So I'm just going to start by talking about how the key press FSM works. So the key press FSM corresponds to this tiny FSM, 2 states, which works like this. So in the lock controller module, if you press the key, it feeds immediately into a priority encoder, which feeds into the small FSM. So what the small FSM does is every time the key is released, it will send a clock pulse of at most 1 clock cycle to the main module, which encodes the key into 4 bits according to this rule, where invalid is assigned number 14 and none is assigned 1111, which is pretty easy to work with. So, okay, I'm just going to jump into a few test cases. So, I'm going to reset my... So, one thing to note is that before the reset happens, my LED blue is on. But however, because the reset clock cycle is guaranteed to come before the user can do anything, I'm going to consider this not a bug. So you can see if you reset it, the LED goes off. Okay, so let's begin by attempting the lock. So set goes to the set state, I lock it, and then naturally lock goes 1, lock command goes 1, next clock cycle, they go off. Okay, so now let's try unlocking it. So the way that the unlocking mechanism works is down here I have 2 rows. Each one is analogous to a 3-word shift register. So the top row is a user code. It defaults to 314. However, this may be changed by programming. The bottom row is a user input. So the bottom row, every time a number is input, that number is pushed onto this register. 314. It's pushed onto this register. Furthermore, the unlocking mode is associated with a counter. And the only way that user input will be correct is if this number is greater than or equal is 3 and these 2 rows match. This is to prevent hacking, where you can enter 3, 1 as the last 2 numbers of one command sequence and 4 as the first one of your second command sequence, and then these 2 rows will match. However, the length of the user input isn't correct, so it should go to error. But in this case, they do match, and the length is correct. So if I try to unlock it, lock goes 1, lock command stays 0, which is correct. Next clock cycle, they go off. Okay, so as an example of one that goes to error, I'm going to go to, set state, and then I'm going to enter just a 3. So in my shift register, there's a 143, nothing's correct, not even the length is correct. So if I try to unlock it, I am sent to this error state and the red LED is raised. Okay, so now let's try the programming. So I'm going to set state and then I'm going to program it. Okay, so the way the programming works is because the programming mode will only be successful if the user input is a string of 12 words, and so I felt there was no need for a data path, so I just kept everything inside of a control FSM, which is reflected in these many states, I think around 12, to do the programming. So I'm going to do the programming code 161. Let's take a look at it. It's over here, and now I'm going to finish this up. 8 0 3, change the code to 3 3 3 3 3 3. Okay, so I gotta finish this up, finish the programming. Okay, so we're back in the waiting state. That means that the program was successful, and as we can see in the top row here, the user code was changed to 333. So now I'm gonna attempt to unlock it just to show it works. 3 3, just as many 3s as I need, because as long as the last 3 digits are 3s, as we can see here in the bottom row, then if I unlock it, it will be successful. Lock goes 1, lock command stays 0. Next lock cycle goes back to the waiting state with no error raised. So I'm going to assume that your testing script will cover a lot of the corner cases that I wasn't able to cover right now, so I'm just going to stop here. Thank you for listening.